Hey students, welcome to the first lesson of Unit 2. In this lesson we're going to be looking at relations and functions, and we'll be reviewing these three learning goals. Number one, we're going to learn or review domain and range of a relation. We're going to distinguish between a relation and a function. And finally we're going to learn function notation and how to evaluate functions. Let's start off by defining the word relation. A relation is a set of ordered pairs. Now these ordered pairs have some sort of relationship to each other, so we call them a relation. A set of ordered pairs can be shown in a table, a graph, an equation, or in a mapping diagram. Now when we think about these ordered pairs, the set of x values is called the domain, and is also referred to as the input, and the set of y values is called the range or the outputs. So something from the domain is input into whatever this relation is, and the output or the range is what comes out of it. Now we distinguish between two different kinds of relationships or relations. A relation with distinct points is called discrete. A relation with connected lines or curves is called continuous. So when you have a relation when each element of the domain is paired with exactly one element of the range, we call it a function. So again, to emphasize, a relation in which each element of the domain is paired with exactly one element of the range. So again, the key word there is exactly, and each element of the domain is paired with exactly one element of the range. Here's an example of a relation that would be a function. So notice this one happens to be a discrete relation, but we have four ordered pairs, and notice in each case there was a unique x value that's paired with a unique y value. So there's exactly one element, and the domain is mapped to one element of the range. Now this discrete relation is an example of something that would not be a function. We have these four ordered pairs, -7, 2, 6, 1, -3, 9, and 6, -2. Now notice I said 6 twice. So there's the same x value that in the two different cases are paired with two different values. And so if you had a specific input of 6, it's kind of not predictable exactly what the output could be. It could be 1, it could be -2, and what that's telling us is this relation isn't functioning correctly. So we would say it's not a function. So we're going to go ahead and take a look at some of these examples, and in the directions they say find the domain and range of each relation. Now we said domain was inputs or x values, and range were y's or outputs. And then we're going to determine if the relation is a function. If it is a function, we're going to state whether it is one-to-one. So we'll talk about what it means to be one-to-one. So let's go ahead and look at these examples. So as we said before, the domain are the x values. And so if we just simply went up here and identified all the x values, and usually when you do the domain, you'll list them in these kind of fancy brackets, and we list them in numeric order from smallest to largest. So the smallest x value is -1, then 0, then 4, then 6. And now my range would be my y values, my outputs. So those are going to be my outputs. And again, it's just kind of the norm to put them in numeric order. So smallest to largest, there's -9, then -5. The next one would be -2, and then 3. And again, if we want to know if this is a function, we just have to look to see if the x value repeats. And if it does it show that it's mapped to a different y value? If that's the case, then it's not a function. But clearly, our x values don't even repeat. And so, yes, this is a function. There is no repeating x value that appears with a different y. So that's a function. Now notice with this next example, if we went through and identified that domain, the smallest one is -3, then 5, and then 5 again. So see, 5's repeating, which in case of listing the domain, we do not list it twice. We don't want to repeat. So we would just list it the one time. and that's going to tell us something about whether this is a function or not. So my outputs, or my range, are these y values. So the smallest one appears to be 0. Oh, nope, sorry, -6. Then 0, then 2, and then 4. And so this is sort of a red flag because there's less numbers listed in my domain than there is the range. That means there must have been one domain value that repeated, and that's really that trigger that tells us this thing is not a function, because when I input 5, I don't know what's going to come out of that relation. I don't know if I'm going to get 2 or if I'm going to get -6, and so that tells me it is not a function. There is still some relationship between the points in the ordered pairs, but it's just not a function. Okay, so this is even easier to do when our ordered pairs are listed in table form. Because we can clearly see what the x values are. So taking a look at 3, our domain, again, we're going to just take the x values. We'll take this column and just list them out in numeric order. -4, 0, 2, and 7. And then our range values, again, the y's. The smallest one is -1, then 3, then 3 again. So I'm not going to list it again. Oops, and I definitely did this in wrong order. My fault. So the -8 was the smallest, then -1, then 3, and then the 3 is repeating, so I'm not going to list it. Now, does that mean this is not a function? Well, actually, no, this still is a function, because the one that we are most concerned with is the x. We can't have the x, or the input, be the same but get a different output. But we might be able to put different x values in and get the same y. So this actually is a function. So again, what we're looking for is repeating x's. It's okay for the y to repeat. We just can't have the x or the output or the range values. I'm sorry, we can have the range values repeating. We just cannot have the domain or the x values repeating. So it's pretty straightforward. If you want to pause and try number 4 as a you try question, just to test your understanding, you could pause the video now here. And list out your domain and range and see if you think the relation listed in number 4 is a function. Pause the video now. So there's the domain and the range, and yes, this is a function. Let's go ahead and turn the page. Now, these next examples show a relation in a mapping notation. So we mentioned that earlier, mapping notation. So mapping notation, you'll see just these little circles of sets of numbers, and you can see that clearly this first circle here, this is the x values, and so those we'd list out as our domain. So our domain values are -4, -2, and 5, and our y values, which are in the other cell here, are 0, 3, 7, and 9. Now we talked before about how a lot of times there was a red flag when you have less numbers in your domain than there is in your range. And the reason why was if you looked right here, there was this mapping of 5 both onto 7 and onto 9. And so when you use mapping notation, this is that signal that this is not a function. So this is not a function, and that's because this is reflecting that there's 2 ordered pairs that have the same input of 5 and 5/7 is an ordered pair, and 5/9 is an ordered pair, and so then we have that, again, repeating x value, which cannot happen. So that's not a function. Let's go ahead and pause the video now and try example 6 as a you try to test your understanding. Pause the video now. And just take a moment to check your answers on the you try. So we've seen how to identify the domain and the range and whether something is a function of a relation by looking at ordered pairs, by looking at a table of values, by looking at a mapping diagram. But what about if we had the graph of a relation? How would we tell by looking at a graph? Well, there's this thing called the vertical line test. And in order to be a function, a vertical line cannot pass through more than one point in the relation. So if you looked at the relation graphed out and you took and examined the graph as you went from left to right to see if there was any place where you could drop a vertical line down through that graph and it would hit the graph more than one time, that would indicate that there is more than one ordered pair that has the same x value. So that would mean it's not a function. Here's an example of a graph that would indicate a relation that is a function. So I just randomly drew a graph, but just a curve of some sort that no matter where I drop down a vertical line, so I'm just going to show you a few of them, at no place on this graph will I see it cross more than one point on that curve. Notice there's just 1 point right here, 1 point right here, 1 point right here, and 1 point right here. And so when that happens, we would say that that relation is a function. Now this is an example of a relation that would not be a function. And hopefully you can see clearly why that is, because at almost every point but one, where I drop down a vertical line, you can see that this is actually crossing the graph 2 times. So there's one here and one here. And if I actually identified points that these might potentially be, that point here and that point here, notice I have to go right the same amount to get to each of these points, so they would have the same x value. Like, for instance, this point right here could be at 2, say maybe 2, 2, and then maybe this point down here might be at about 2, -3. So you can see there's that repeating x value with a different y value, and that indicates that this relation is not a function. Let's go ahead and look at a few more examples. Taking a look at number 7, notice that number 7 is just a series of 5 different points. So there's a point right here, a point right here, a point here, and a point here, and then finally a point down here. So to identify the domain, what I have to do is look at each one of these points and look at its ordered pairs. So I'm just going to list out the ordered pairs on the graph. I'm going to pause the video to do that. Now, in order to list out the domain, I just have to go through and every x value that I see, unless it's a repeating one, I'm going to list it down. And so I can see the smallest one as I move left to right is -3. And then as I slide over, the next x value I see is 0. And then I see a 2. And then finally a 4 is the largest x value. Now with the y values, I actually want to list them out smallest to largest. I want to look low and then work high up the y-axis. So the lowest value I can see is way down here, that point down here right there, and it has a y value of -5, so that's the smallest range value. Then as I slide up, the next one I see is a, oops, and we forgot to write that, I forgot to write that as a -2, so sorry, that's a -2 right there. So the next one is -2, and then -1, and then there's a 1, and then all the way up at that top point is a 4. Now again, you can kind of see that sort of red flag. The domain only had 4 elements in its set, and the range had 5, and the reason why is right here, along this vertical line, we have 2 points that share the same x value, but with different y values. So this is an example of a relation that fails the vertical line test. So I'd say this is not a function. And then the reason why is it fails the vertical line test. So we'll sometimes abbreviate that like this, fails the VLT. And then to really emphasize that, we can actually show these 2 ordered pairs that where they have the same x value but different y values. What about with number 8? Now with number 8, notice there's not any specific points that are identified. This is just a continuous graph. It's a line of some sort. And so how do we specifically give a domain? Well, when we have something continuous like that, we can't actually list out all the specific domain points. And so instead, what we'll do is we'll see if we can refer to a set of numbers like we've studied, say, like the natural numbers, the real numbers, those kind of things, and to describe. And if you look at the domain, we're going to want to look left to right. So what I'm going to do is I'm going to look left to right, because that's where the x values are, and notice that this graph is continuous left to right, and I could pick any particular input, x value, and I know there'd be a point on the graph. Like let's say I identified at, say, +2, I know up on the graph there is a point where x is +2, or if it was -2, it would be over here. And so really I couldn't list them all out because it's really all real numbers. So we would say that the domain is all real numbers, and we could use that all real number symbol. Now in the case of the range, we want to look high to low, so we're going to scan starting lower on the graph and scan up, and you can see that there is no cutoff. I mean, we're going to get outputs really as high as we could go and outputs as low as we could go. And so again, we know that the range is all real numbers, because really we can put any real number in this linear function and we can get anything out. And again, this I did call it a function, and that's because I'm already looking ahead. This is a function because you can see at any point here I can drop down a vertical line, and you can see at no time is it going to ever hit more than 1 point. And so this is a function, and it passes the VLT, so passes the vertical line test, and that's kind of my confirmation that it is a function. So how about example 9? So this time with a domain, when I look left to right, notice as I'm looking left to right, this graph actually ended right here. It doesn't go any further left than right here. But then it actually goes, because those lines indicate like the graph is going to continue out to the right, and it doesn't appear to stop anytime. That's why it's got the arrows saying it's going on forever. And so the smallest x value that I could see, that I could possibly get, is at that spot, which is at -4 and -1. And so that's the smallest possible x value that I have is -4. So I would say that the x values are always greater than or equal to -4. And that's a way I can quantify that there's infinitely many numbers in the domain, but that the smallest that they ever get is -4, but they'll go on getting bigger and bigger forever. Now what about the range? Now the range, as you look high to low, again, the graphs have arrows going, indicating they continue going up higher and higher and down lower and lower. And so with this one, we could say this is all real numbers. Now this graph is not a function, and you can see that in some parts of the graph, it will fail the vertical line test. So if it happens even one time, the relation is not a function. So this is not a function, and you could identify a specific pair of points where the x values are the same to give support. Like here at -3, 2, and this one here at -3, maybe like -1.5, something like that. And it's not so important that we get the exact right coordinates, as long as we know that you can clearly see they're on the same vertical line, so they have the same x coordinate of -3. On example number 10 now, so example number 10 for our domain, when we look at that, there is a distinct place as you're looking left to right that this graph ends. It only goes left to right in between that little interval. And so in order to give the values that are in this domain, I have to see exactly how far down to the left does it go. And this is that ending point here, and this is the ending point to the right is right here. So if I can identify what that highest x value is and lowest x value, and you can see that these lines here cross at -2, which is the smallest number, and up here at, let's see what that is, looks like +5. And what that's telling me is that x can be anywhere between -2 and 5, including those. So it'd be less than or equal to 5, but greater than or equal to -2. So sometimes we have to write our domain as a complex inequality. Now if we want to look at the range, you can see that the highest this ever goes is right here, and the lowest this relation ever goes is down here. And so that highest value up here is at about, let's see, that looks like it's at +4, and this lowest one is down here at -2. And so we could say that the y values are between -2 and 4, so it must be less than or equal to 4, but greater than or equal to -2. And again, you can use one of those complex inequalities to express that there are infinitely many values in this output, in this range, in other words, but they just all lie between -2 and 4. And clearly we can see that this is not a function. There's just one specific example where this shows that it fails the vertical line test. So no, this is not a function. Let's go ahead and turn the page in the notes. Now this first section of this next page is something we're going to reserve for when we're together in class. Because what we're asked to do in this section is to use our graphing calculator to graph these equations and to look at those graphs and identify the domain and range and tell if it's a function. And so what we'll do is we'll save these for when we meet in class, and we'll just continue on in the notes to the next section, and we'll come back to this when we see each other. So let's look at this bottom part of this page. So we're going to talk briefly about function notation. Equations that represent functions are often written in function notation. Now, we've seen, we've written functions like this, y equals 2x plus 7. That actually turns out to be a function. It's a graph of a line with a slope of 2 and a y-intercept of 7. But when we use function notation, it would look like this. And what this is saying is that this relation is a function of whatever the input x is. And so it says f of x is equal to 2x plus 7 instead of saying y equals 2x plus 7. So in the place of the y, we put in f of x to show that y depends on whatever x was. So we would say that x is the input and f of x is the output. Function notation is specifically useful for finding a value in a range that corresponds to a certain domain value. And it's also a nice shortcut way of saying we want to substitute a certain value in as the input. So, for example, if f of x is equal to 2x plus 7, and we ask you to find f of negative 3, that is shorthand notation for saying substitute in negative 3 and for x into that relation and find the value. So f of negative 3 says substitute in negative 3 in place of x and find the value. So if we did that in this case, that would be 2 times negative 3, which is negative 6 plus 7, which equals 1. And so we would say that f of negative 3 equals 1. And that's just another way of saying the ordered pair negative 3, comma 1. Input was negative 3, and the output turned out to be 1. Let's turn the page. So in this section, we're going to use these two different functions. F of x equals negative 5x minus 14, and g of x is negative x squared plus 9x minus 1. And these are just two different functions. Sometimes we'll call function f, and sometimes we'll call it g or h or whatever. The letter doesn't necessarily matter. It's just to distinguish one relation from another. And so if I ask you to find f of negative 9, that means that I'm going to take this negative 9 and plug it into the function f. Whereas see how some of these say g, like this number 3 says g of 0.4. That means you're going to plug 0.4 into the function that's defined as g. So f of negative 9 means I'm going to take this negative 9, and wherever I see an x, like right here, I'm going to plug in negative 9, and I'm going to find the value, which will then give me that ordered pair. So this would mean that the ordered pair negative 9, and let's see what we get. Negative 5 times negative 9 is positive 45, and positive 45 minus 14 is 31. So my output is 31, and so f of negative 9 equals 31, or the ordered pair negative 9, 31. Let's go ahead and try one with function g. So number 3 says g of 0.4, and what that means is I'm going to go ahead and take 0.4, and I'm going to substitute it anywhere I see in the function g. Now, you want to be careful when you're doing substitutions in, just be sure to use parentheses. That way, make sure that the correct order of operations are followed. And so I'm going to go ahead and plug 0.4 into each place. So I see an x. Now notice I put it in 2 places because there were 2 places where x appeared in this function. And I'm going to go ahead and use my calculator to calculate that. And if you'd like to do that, go ahead and pause the video and try it yourself. And when I got a value of 2.44. So g of 0.4 is 2.44, and that indicates I have an ordered pair of 0.4 and 2.44. So what we're going to do at this point of the lesson is we're going to divide this lesson up to right underneath 6, And anything past number 6, we're going to wait and we'll pick up in class together. So 6 to the end, 6 all the way through 11. But what I'd like to have you do now is pause the video and try 2, 4, 6, and 5. And tune back in and see how you did. So we're just going to designate these as you try questions. Once you've tried those and checked them, then we'll end class for today and we'll pick up where we left off when we see you. So pause the video now and try those 4 you tries. Okay, so thanks for giving those a try. One thing that was a little tricky in this set of you try questions, number 5, notice, had a difference between 2 functions, f of 1 minus f of negative 4. So just simply evaluate the 2 functions separately and then subtract. And then with number 6, we were asked to find the product of 2 and g of 12. So you had to find out what g of 12 was and then multiply by 2. And oops, I'm sorry. I think I wrote down the answer for one of the ones lower down for number 6. Nope, that was right. I'm sorry. Yes, it was. Negative, this part right here was negative 37. And then doubling it does make it actually negative 74. So that was correct. So we've got negative 31 halves for number 2, or negative 15 and a half. Negative 113 for number 4. Number 5 is negative 25. And finally, number 6. So that does it for the video part of the lesson, and we'll pick up and complete the sections that we've left for class when I see you.